Good evening, everybody, and welcome. My name is Annie Hodgson. I work in the chemistry department at the University of York. Just a few technical notes before we begin tonight's talk. If you are watching live, you can ask questions using the Q&A button on your screen. This will be available throughout the event, so questions can be asked at any time. Should you have any technical issues, such as a loss of Wi-Fi, you can rejoin the event using the original link. Please also remember that today's talk is being recorded, so you'll be able to watch it again. This event forms part of the University of York One Planet Week, which runs every year to celebrate sustainability research and work completed at the university. The title reminds us that we live on a planet with finite resources and that currently we are living beyond these limited means. I have great pleasure in introducing our speaker for the evening. Professor Robin Perutz is a friend and colleague from the Department of Chemistry at the University of York. After studying in Cambridge and Newcastle, Robin worked at Mülheim, Edinburgh and Oxford before moving to the University of York in 1983, where he was promoted to Professor of Chemistry in 1991. He became an emeritus professor in 2020. Robin studies chemical reactions of compounds of metals stimulated by light in order to understand catalysis and develop solar energy. He became a Fellow of the Royal Society, the UK's National Academy of Sciences, in 2010. For many years, Robin has been active in the Women in Science agenda and in supporting students with disabilities. He also has a long-standing interest in human rights of scientists fleeing conflict. This evening, he will tell us about the scientists, explorers, science fiction writers, poets, artists, and playwrights who foresaw climate change and how the world did not listen to them. We will be going back 200 years in time and will explore the globe as we do so. So please put your virtual hands together to welcome Robin Perutz with his talk, Those Who Foresaw Climate Change, but the World Did Not Listen.
Well, I'm going to dive straight in, and I'm not going to start with carbon dioxide. I'm going to start with how climate change has been manifest through deforestation and retreat of the glaciers. And whoops, where maybe you can help me a moment, because I'm getting my ribbon blocking my view. Just see if I can deal with that. Don't think so. Well, I will go ahead. I hope you can see better than I can. So we're going to begin with Alexander von Humboldt. So Alexander von Humboldt, very famous German scientist, writer, politician, all sorts of things he did. He went as a young man to South America and traveled in Venezuela along the Orinoco in 1799. And he was interested in absolutely everything he saw. And later on, 30 years later, he traveled in Russia, right as far as the Mongolian border. But already while he was in Venezuela, he explained the fundamental functions of the forest, but the ecosystem and the climate. So what he wrote was the wooded region acts in a threefold manner in diminishing the temperature, by cooling shade, by evaporation, and by radiation. You could probably find the exact same words almost in a geography textbook today. By the way, if you are interested in Humboldt, there's a fantastic biography of him called The Invention of Nature, written by Andrea Wolf. So how did he know about what went on? Well, what he saw, what his conclusions really came from observations of Lake Valencia in the north of Venezuela, where he saw the effect of deforestation and realized that forests are closely linked to the rainfall. And he wrote in more detail than I showed you before, when forests are destroyed, the springs are entirely dried up, the waters falling in rain are no longer impeded in their course, and instead of slowly augmenting the levels of the rivers by progressive filtrations, they furrow during heavy showers the sides of the hills and form those sun inundations that devastate the country. So forests control rainfall. And at the right, you'll see a picture of tropical forest I took from the air in Panama when I visited in 2016. And if you want to see how closely linked the forest is to rainfall, there's no better place than the Panama Canal, which I also visited at the same time. Panama Canal, if there's no forest, there's no canal. Exit canal. Why is that? Well, the forest creates the rainfall. It maintains the rainfall. It prevents the runoff of sediment, and the canal actually consumes vast quantities of water. These figures are for the older canal. 200,000 cubic meters every time a ship passes. That's what's transferred. So strangely, the US canal zone, which persisted until 1999, was actually very good for the forest, though for a long time it was for the wrong reasons. It was for military reasons. Later, the US realized how important the water was. So the couple of pictures are below. One, you can see the ships, and the other was just from the hotel I was staying in. Just below the hotel, you can see some bushes, and there a ship passing in front. So the forest really matters. So Humboldt had huge influence, and particularly in America. And I've singled out two people who he influenced. The first was called George Perkins Marsh. He wrote a book in 1864, Man and Nature, or Physical Geography as Modified by Human Action. So he had visited Europe, and he was concerned that the US, if it wasn't controlled, will turn into the dismal place that Europe was. He described Europe's land was being farmed into a desolation almost as complete as the moon. Now, this was in the 19th century. It's quite hard to believe this when you look at what's happened since then. Now, the other person better known is John Muir. John Muir, if you've been to places in Scotland, you might have come across the John Muir Trust. He was a Scot originally, but moved to the US. He was quite a maverick, way out sort of guy, but he was a brilliant campaigner, and he treasured Humboldt's books, and his copies still exist with all his annotations. And his favorite place was Yosemite, and he campaigned for it to become a national park. Now imagine you receive a letter from the President Roosevelt, to John Muir, can I come on a camping trip with you in Yosemite? And that's what happened. And in due course, that led to the establishment of the Yosemite National Park in 1890. He was extraordinarily influential. And I've got another quote from John Muir. I'm glad that I got to California soon enough to see the state in all its untrammeled beauty. I have walked 500 miles through the San Joaquin and Sacramento valleys when they were an unbroken mass of golden blooms. Now, he's not exaggerating when he talks about walking 500 miles. Anyway, the photo at the right I took in Mariposa Grove and Yosemite, showing the sequoias. Really, we would not have the sequoias but for John Muir, but for Humboldt, who influenced him so much. So that is crucial, that forest. So a few weeks ago, I watched Uncle Vanya, Chekhov's famous play, on BBC4, with Vanya played by Toby Jones and Astroff by Richard Armitage. And I was very struck by a little piece where Dr. Astroff laments the effect of deforestation on the climate and the environment, not just the environment, on the climate. So that was, Uncle Vanya was written in 1898. Again, the message has got through about forests and climate, though I didn't find any evidence that it went through Humboldt. What I found was that Chekhov was influenced by a climatologist called Voykov, who had written a book on the influence of the forests on the climate in 1878. So already very early. So you can see Chekhov, by the way, on the right of on the picture on the right from the Tretyakov gallery. So let's move to glaciers. There was a wonderful exhibition at the York City Art Gallery in 2019 of paintings and drawings by John Ruskin and by a modern artist called Emma Stibben, who followed through on what's happening to glaciers. A brilliant exhibition. So John Ruskin was another 19th century polymath, perhaps best known as an art critic, but he was an artist himself, and he also was interested in science. So the picture at the right is of the Glacier des Bossons near Chamonix, which you can see that then when he drew this in 1849, the glacier came right down to the village. But he compared the same glacier on several visits between the 1830s and 1874. And at the end, he writes, "I was able to cross the dry bed of a glacier, which I had seen flowing 200 feet deep over the same spot 40 years ago." So the glaciers were warming up and retreating. And he drew attention to several familiar themes now: fossil fuel burning, pollution resulting, unsustainable development, and the effect on nature. He thought he was talking, that nobody was listening, and it all fell on deaf ears, but he was way ahead of his time. So let's switch now to the greenhouse effect. And it's probably where you thought I would begin. Just in case you have any doubts about what the greenhouse effect really is, here's a nice picture from the Environmental Protection Agency in the US. You've got the sun's radiation hitting the Earth. Some of it's reflected, much of it is absorbed. And then the Earth that is heated re-radiates infrared, and that heats the atmosphere. So some of the infrared radiation passes through, some is absorbed by the greenhouse gases in the Earth's atmosphere. So that's the principle of the greenhouse effect, but we'll see more as we progress. How does this work? What's going on? Well, the first person I came across who really investigated this was Eunice Foote, an American woman in 1856 who shone sunlight onto gases, onto air, hydrogen, and CO2, and she demonstrated that there was a much greater heating effect on CO2. So she writes, an atmosphere of that gas would give to our Earth a high temperature, and if, as some suppose, at one period of its history, the air had mixed with it a larger proportion than at present, an increased temperature from its own action must have necessarily resulted. In other words, she was predicting that more CO2 would mean more heating. The trouble with her experiments was that she just used unfiltered sunlight, and she wasn't really looking at infrared radiation. And the other thing is that she wasn't making it quantitative. But nevertheless, very good start. And after all, these gases are transparent to visible light. So it's not that bad a mistake. So now we come on a few years later, I think already in 1859, this was quite advanced, to John Tyndall. And John Tyndall, let's see if I can do a bit more with this pointer. I don't think it's going to work. No. John Tyndall went much, much further than Eunice Foote. What he did was quantitative and concerned infrared itself. And so he devised apparatus. I'll show you it in a moment, though not in detail. And he devised apparatus where the gases could absorb the infrared and then radiate again onto a detector. And he measured this with a galvanometer, in other words, a meter measuring current. And what you see are his results there. It says at 5 inches pressure. This corresponds to the pressure of the gas. So he's standardizing the pressure of the gas, and there's a series of gases. We all need a bit of a translation. Carbonic acid is carbon dioxide, and olefiant gas is ethylene. So what he found, you can see there, that there was negligible deflection of his galvanometer for air, oxygen, nitrogen, and hydrogen. Then carbonic oxide, that's carbon monoxide, 18 degrees. Carbonic acid, that was our CO2, 25 degrees. Nitrous oxide, 44 degrees. And this olefiant gas, in other words, ethylene, a mammoth 61 degrees. So he's seeing quantitatively that these gases at the bottom really have a big effect. The picture, by the way, was drawn in 1850 by a friend of his, Thomas Hurst, and the comment is, Tyndall and friends climbed Beacon Hill at Halifax, and Tyndall remarks, Tom Hurst entrapped me into having my portrait taken by him. I was tickled by that language. It's the sort of language we'd use about a photograph, but here it was the drawing. So here's Tyndall's kit, quite complicated setup, as you can see. And what Tyndall predicted was any variation in atmospheric CO2 would change climate. Tiny amounts of hydrocarbon would also change the climate. Such changes may have produced all the mutations of climate which geologists reveal. Well, I don't think we'd go along with all for reasons you will see in due course. but certainly the effect of CO2 through geological time on climate, yes, and that other comment, really important, tiny amounts of hydrocarbon would also change the climate. And that, of course, is what we're worried about when we talk about, oh, I've managed to move this now, that's good. I should have tried a bit harder before. Such changes would have, we're talking about these days with methane and so on, tiny amounts of methane really matter. So let's go on. Now, why won't this work? There we are. So we now come to another pioneer quite a lot later, into the 1930s, but we've jumped a bit. That's better. Sorry. Start that again. And the next pioneer is Arrhenius. He's very famous among chemists for all sorts of things that he did, but critically, one of them was the greenhouse effect. And what he did was think, can I predict how much CO2 would be needed to cause the glaciers, to cause the Antarctica and the poles to melt? What would I need to reduce the temperature so we had another ice age and so on? That's what he wanted to calculate. And so he needed a mathematical model. Now, these days, you all know what a mathematical model is. We get plagued by talk about mathematical models on the radio for COVID. So he made a mathematical model and calculated what would go on. And the first important conclusion was, he wrote like this: if the quantity of carbonic acid increases in geometric progression, the augmentation of the temperature will increase nearly in arithmetic progression. Well, that's a pretty much of a mouthful. And these days, we would probably just say it goes up logarithmically. So the temperature goes up logarithmically with the amount of CO2. Well, what he reckoned was that the temperature in the Arctic would rise about 8 degrees if CO2 increased 2.5 to 3 times its present value. And the temperature between 40th and 50th parallel of latitude would lower 4 to 5 degrees if the CO2 was reduced by 55 to 60%. So that's quite dramatic changes that he's predicting. A first quantitative go at what's happening. Now, I'm sorry for the glitch. We move on to calendar. This is a picture of Guy Callendar that is from the University of East Anglia archive. He was a steam engineer, but obviously very interested in meteorology and what was going on. And he thought, if I use the data from weather stations, I can see how much the temperature is increased, and I can relate that to the amount of CO2. So he got data from 147 weather stations and calculated that the temperature had gone up 0.3 of a degree between 1880 and 1935, and related that to the increase in CO2. So actually, he was quite accurate already then. That seems remarkable. And then he went on to, again, do the heat balance calculations, but with much better data than Arrhenius. And he attributed half of the temperature rise that had occurred between 1880 and 1935 to the CO2 increase. And he then went on to predict that how much the temperature would rise in the next 65 years. And you can see his graph on the left, which shows you the surface temperature versus the amount of CO2 in the atmosphere. The trouble with his predictions was that he grossly underestimated the amount of fossil fuel we would consume. So the predicted rise was much lower than what we've actually seen. But he was very much on the right path to where we are today. So at this point, I thought we should have a bit of an explanation of why carbon dioxide, methane, and nitrous oxide are such potent greenhouse gases, and why oxygen and nitrogen do nothing at all. Strangely, when you look up at this question, you don't of greenhouse gases, there's much of a mention of what's special about CO2 and methane and nitrous oxide. So how did we get to understand that? Well, certainly it was quite out of the question for Tyndall to understand that, because it needed James Clerk Maxwell to come along and tell us about electromagnetic radiation, how light and electromagnetism are related. It also needed Max Planck to tell us about quantum theory. So those were two essentials before we could get going. And the way we put it now, and I'll explain this, so don't get put off by the science. I'll try and explain this very simply. What we say now is this. What happens when infrared radiation is absorbed is that the molecules vibrate. So they go backward, the atoms go backwards and forwards. That could happen in principle with oxygen as well as with carbon dioxide. But absorption is only possible if the dipole moment changes during vibration. So I'll have to explain what that means in a moment. And the greenhouse effect is really strong if absorption occurs in a region of the spectrum where water vapor does not absorb. There's always water vapor absorbing, so if it's the same region, it doesn't really matter. But if it's a different region of the spectrum, it matters immensely. And of course, the other thing is if gas accumulates in the atmosphere. So I will try and explain a bit further. So carbon dioxide, if you can see me on the screen, you can have a vibration where the oxygens stretch together, or one where one bond compresses as the other stretches. Two possibilities. Now, oxygens attract electrons rather more than carbon. So there's a tiny little bit of electric charge on each of the oxygens. But if they stretch together, there's no change in the perfect balance between the two oxygens. But if one stretches and the other shortens, yes, there's a big change and you get strong absorption. So that's why CO2 absorbs infrared. And with methane, and there's a picture at the bottom, you get the same sort of thing. If one bond stretches and three shorten, you get strong absorption. But if you have oxygen and nitrogen, when they stretch, there's no net charge on the atoms anyway, and nothing changes. So they cannot absorb infrared. As for argon, that's just one atom, so it can't vibrate in the first place. So the three big components of the atmosphere, oxygen, nitrogen, and argon, do nothing for the greenhouse effect. And the very small components, carbon dioxide and methane, really matter. So, final little bit on this science. I've got just an infrared spectrum here of air, a bit more explanation. This is like spreading out visible light into red, orange, yellow, green, blue, and violet, but this time we're doing it for the infrared. And what you see on the left are some really zigzags. It looks like noise. It's not. It's strong absorption by water vapor. And then there's another section with strong absorption by water vapor. But in between, there's that big spike where carbon dioxide absorbs. So absorption is going downwards. And then there's a little spike at the right, which is again carbon dioxide, and that's where carbon dioxide bends rather than stretches. So carbon dioxide fits all of these criteria. It's well away from where water absorbs. It's a strong absorber. And the same is true of methane and nitrous oxide. So really, Tyndall looked at the right set of gases. We're really worried about hydrocarbons and nitrous oxide. He just used ethylene instead of methane, but we'll let him off that. Now, if you're going to say that the climate is changing, you better know what it was like before. It's no use just looking at it now. We've got to think about past climates. And now, already in the 19th century, geological evidence piled up for different climates in different places. But the person or people who really put this together were Alfred Wegener, Vladimir Köppen, and Milutin Milnkovic. Now, Wegener is extraordinarily famous. He's the hero who proposed continental drift, and all those horrible physicists poo-pooed what he said, thought they knew better, said this was utter rubbish, and poor old Wegener didn't live to see his theories vindicated. That had to wait until the 1960s. But in addition to the continental drift, Wegener studied past climates, and he teamed up with his father-in-law, Köppen, and they produced this book you can see on the left, The Climates of the Geological Past. It was published in 1924. This cover picture is of a recent translation into English. And they went systematically through geological age after geological age, analyzing past climate in a pretty quantitative way. And they roped in somebody to help them, and that was Milnkovic. And Milnkovic had just shortly before that calculated what would happen to the Earth's climate as a result of changes in the Earth's orbit and its angle of tilt and movement of the poles. Now, he knew already that all of these things happened on a regular basis. I'll show you a picture in a moment. And so he was able to predict a cycle of climate change and when the ice ages, past ice ages, had been. He was actually an engineer from Serbia, And he was obviously stuck with nothing to do, not because of a pandemic, but because he was a prisoner of war. And while a prisoner of war, he developed these ideas. So here's on the right, you can see a diagram with what are now called the Milnkovic cycles. The Earth goes around the sun in an ellipse, which is not quite a perfect circle. And it changes. It's much exaggerated in that picture. The difference between circular and elliptical changes with time. The tilt of the Earth changes with time, and the poles wander about, and they move with time. And that's what Milnkovic was calculating. And you can see on the left his graph, all these zigzags. So what he's doing here, I've reproduced half of it. It went back 600,000 years. This picture only goes back 300,000. And he's calculating the amount of solar radiation at different latitudes. So it's really meant to be a three-dimensional graph, but he couldn't show that so easily then. And you can see there's some severe dips which are shaded. That's when he was predicting that there would be an ice age. So he's making all these predictions. It's all put together in this book with Wegener. He's not an author, strangely, but in fact, he contributed a great deal of the book. I don't know what the story was there. So now we're getting a bit more modern. We move on to Charles Keeling, and this is really the beginning of the modern era. So in 1958, Charles Keeling had the idea that he would measure the amount of CO2 with time, year by year. That sounds a pretty obvious thing to do. It sounds ever so simple, but people were already skeptical that it was possible then to disentangle the seasonal variation and the year-by-year variation. So Charles Keeling chose to do this on Mauna Loa in Hawaii, big volcano, 3,000 meters plus high, very dry atmosphere, very stable, well away from any industry or anything that would disturb. So that's what he set out to do. And he continued doing this or supervising the measurements until he died in 2005. But in fact, of course, it's continued now. And you've probably all seen this graph. So you can see a blue line and a yellow oscillating line superimposed on it. And if you expand that out just to a few months, that's what you see above. And you see there's a seasonal variation. That's producing the oscillation. It goes up in the CO2 goes up in winter when there's less photosynthesis by plants, and it goes down in summer. But superimposed on that's superimposed on the general trend, and the general trend has taken us from about 280 parts per million when he started to about 400 parts per million now. So, by the way, he used an instrument invented by Tyndall, at least to start with. So, not long really after he started, the National Science Foundation stopped supporting his research. They called the outcome routine. What's the point of this? I've heard that sort of comment before from people in high places who don't understand the importance of systematic measurement. Anyway, the National Science Foundation in 1963 used his research, Keeling's research, when it started warning of rapidly increasing greenhouse gases. So totally hypocritical. So the last little section, I just want to come to mitigation, solar energy and the hydrogen economy. I can't do without solar energy. As Annie said, that's my own pet. Now we come to Jules Verne, not 20,000 leagues under the sea. Whoops, sorry about this. But another book that he wrote called The Mysterious Island, and that written in published in 1874 predicts the hydrogen economy. I'll see if I can read this out. I've got a problem at the moment. Maybe I can minimize this. Ah, that's better. Right, now I can see my screen properly. And what will they burn instead of coal? Water, replied Harding. Water, cried Pencroft. Water as fuel for steamers and engines? Water to heat water? Yes, but water decomposed into its primitive elements, replied Cyrus Harding, and decomposed doubtless by electricity. Yes, my friends, I believe that water will one day be employed as a fuel, that hydrogen and oxygen, which constitute it, will furnish an inexhaustible source of heat and light, of an intensity of which coal is not capable. Someday the coal rooms of steamers and the tenders of locomotives will, instead of coal, be stored with these two condensed gases, which will burn in the furnaces with enormous calorific power. Water will be the coal of the future. Well, how about that for prediction in 1874? Well, as for using condensed hydrogen and oxygen, I think that's confined to Saturn V rockets and the like. But of course, we're moving towards the hydrogen economy. We won't bother with liquefying it, though. I can't imagine you having liquid oxygen and liquid hydrogen stored at home. But an amazing prediction. So another big prediction came from a scientist called Chmi Chan. He wrote in the journal Science in 1912 about his vision for solar energy conversion. And what he wrote was, so far, human civilization has used exclusively fossil solar energy. In other words, fossil solar energy is coal. Fossil solar energy is oil. Would it not be advantageous to make better use of radiant energy? By using suitable catalysts, it should be possible to transform the mixture of water and carbon dioxide into oxygen and methane. It is conceivable that we might make photoelectrical batteries or batteries based on photochemical processes. So photochemical processes, if you're not familiar, that means chemistry driven by light. And indeed, Chmi Chan was a photochemist. As for his prediction about catalysts to transform water and carbon dioxide into oxygen and methane, that's the sort of thing that people like me are still working on now, trying to make into a practical proposition. So we scientists have been trying to do this for well over 100 years since this prediction. We haven't really got it sussed even now. So here is Chmi Chan in Bologna where he worked with all his retorts on the balcony of the lab. So there he did his experiments with lots of sunshine in Bologna to do his photochemistry. And on the right, you can see him delivering his lecture demonstrations with an assistant. So there we are. Lots of predictions, lots of foresight. What actually happened? Well, I'm not going to take you to the present. You probably know lots about that. But here's a little timeline. In 1963, we had that warning from the National Science Foundation. In 1965, there were warnings from President Johnson's Science Advisory Committee. In 1966, his chief scientific advisor, Glenn Seaborg, warned again. And in 1978, or I should say around 1978, people were really beginning to make progress with reconstruction of past climates and see how things have changed. Now, the next one, you may think, oh, this is irrelevant. The 1987 Montreal Protocol. Well, that didn't concern climate change. That concerned the ozone hole and how we could stop the ozone hole growing, indeed set it back on its proper path. And that treaty was signed very soon after the first warnings came. And it was a really successful international treaty. It continues to this day. And one of the people who drove this was Margaret Thatcher. May sound surprising. I disagreed with most of her policies, but for this, she really was a driving force. So 1988, the Intergovernmental Panel on Climate Change was established, and their first report came a couple of years later. In 1992, there was the Big Earth Summit. So Mrs. Thatcher really laid it on thick to the United Nations about how necessary it was to do something to prevent global warming and what catastrophe lay in store. So she obviously tried extremely hard, but as we all know, it didn't get anywhere. Things continued to move ever so slowly and have moved ever so slowly all that time since. That was 1989, so we're well over 30 years since then. So I'll finish just by saying, are we in time to prevent total disaster? We haven't really got any idea whether we can or whether we cannot. But unless we try our hardest, we certainly won't prevent total disaster. So that's what we've got to do. And I will stop there. Apologies for the difficulties with the video there.
Thank you very much indeed, Robin, for a really excellent talk and very thought-provoking. We've got lots of questions that have come through in the chat. I've been trying to sort them into some sensible order, so I will see how many we can get through. First one, just a factual one. You showed a picture of a glacier earlier, and the question was, is this the one that recently died, in inverted commas, last year?
Oh, no. I think there was one in Switzerland that completely disappeared. No, that's not that. This is a much bigger glacier than that, and is still there. Right,
thank you. This is more of a comment, but it's quite topical. It says NASA put a rover on Mars where they predict there used to be a lake. It's tough to think ending up like that we might be ending up like Mars. Sorry, I'll read that again. Tough to think ending up like Mars might be our planet's fate, but without climate change a long time ago, from an oxygen-rich atmosphere, we wouldn't be here now, which is a fair point. I don't know.
Well, I can't comment further, except yes, of course, the atmosphere has changed drastically over geological time. We have oxygen thanks to photochemical reactions, indeed, thanks to plants.
Yes, yay, go plants. A technical question. How did they determine carbon dioxide concentration in the atmosphere historically, and how do we do this now?
Right, well, it's quite straightforward to measure an infrared spectrum now and see what's going on. We can also use other techniques like gas chromatography to measure now, but if you're going to measure the total in the atmosphere, then you've got to do the measurement right through the atmosphere. I'm not expert in this, and I don't know how it's done nowadays, but you've got the same principles available to do the measurement through of the absorption of light through the atmosphere. So you can look at the spectrum as the light hits the earth and determine how much carbon dioxide.
Thank you. This one starts with fantastic talk. Thank you very much, Robin. It says, whilst I realise that the Industrial Revolution was one of the biggest drivers in future levels of carbon dioxide, I wonder what caused rises in nitrous oxide and methane, other than methane being emitted by cows and from melted permafrost. Thank you again.
Right. So nitrous oxide is the greenhouse gas that was really established to be a serious issue only relatively recently. And one source is from fertilizer that is put on farms. There are microorganisms which will turn nitrate into nitrous oxide and also ammonia into nitrous oxide. So that's one source. There are also industrial sources. And I remember a story from a colleague who pointed out that manufacture of nylon produces large quantities of nitrous oxide. And at that stage, nitrous oxide was not a byproduct that you had to declare. And the atmospheric chemists were saying, where's all this nitrous oxide come from? It shouldn't be there according to our calculations. And the answer was nylon production. And of course, nowadays it's captured and it isn't, it doesn't come from that source.
Thank you. Right, we've got lots of questions. I think we've only got really time for one last one. So I've lost the one I was going to ask you now. If you could incontrovertibly influence international policy on greenhouse reduction, what would your two main recommendations be?
Oh, wow. Well, what's needed, firstly, enormous investment in solar energy as well as wind, because that really hasn't been advancing nearly as fast as it could go. So that's one part, and an adjunct to that is also developing better ways of using solar energy. So that's one part. The other part, I think, is really almost the social science side of it, to try to really persuade people that it matters, that because what people see is incremental. They don't see the big change. It's a bit like what we see with, for instance, swallows. In the past, there may have been hundreds and hundreds of swallows roundabout in York. Now, there are only a few. Go on a few more years, and there will be even fewer, but we won't have the memory of when there were hundreds. And that's one of our difficulties with climate change. The memory gets lost. So that's why we really have to work at persuading people as well as doing the science and innovation.
Right. Well, I think tonight you've done your bit for persuading this part of the population. I see that we've got 132 in the talk, so you've made a start. So thank you very much, Robin. So thank you very much for your brilliant talk and for answering all of these questions. I'm sorry, folks, we didn't get to everybody's question, but just not enough time. But I hope you can hear, Robin, the rapturous applause across the internet that I'm sure people are giving you right now. I'd also like to take the opportunity to thank the events team at the University of York, who beaver away behind the scenes to bring us all these fantastic talks. I don't think they get enough recognition, so thank you to them. The recording of this event will be available on the York Ideas YouTube channel, which can be accessed by typing York Ideas YouTube into Google. However, just allow a couple of days or so before it appears. We have just arrived at a weekend, so sometime next week, I'm sure it'll be there. Further information on the university's sustainability policies and One Planet Week are available on the website york.ac.uk/about/sustainability, which Catherine has just popped in the chat if you want to copy that. We very much hope that you will continue to engage with the University of York's open lectures, a full listing of which can be found on our website, york.ac.uk/events, and Catherine's popped that in the chat for you as well. Thank you, Catherine. So that just remains for me to say thank you all for joining us. Thank you for asking so many great questions. Sorry again that we didn't manage to get to answer them all, and hope you enjoyed the rest of your evening and have a lovely weekend, folks. Goodbye, everybody. Cheers. Thanks a lot.